Thanks, Ron, for a very nice talk. So let's take some questions from the audience. So any hand, or you can just unmute and ask a question, please. So today the time is changed, so I think there are less number of people. Apologies for the from us to the speaker. Okay, enough. I guess. Yeah, there were 21, 22 max, but yeah. So any question? So I'll ask question otherwise. So please, some hand raised? No. So let me ask some questions and some comments. So great. So I think you did quite a careful work with. I really like that K minus and K plus. Good demonstration. The paper is published or not yet? Like
no,
you
I'm
had
writing it up now. Yeah.
I see, not right now. Okay, good. So once it is written, you can send me for. I'd like to have a look. So the thing which I want, I've been at it for a long time. This problem, bit earlier. I mean, 20 years back. So I don't. Well, first of all, I think isotropy is an issue. When main magnetic field is present, then isotropy is not there, as you demonstrated with so many careful simulations. But I think that 3/2 is not correct. So I wrote a paper some time back that Kraichnan assumed that the mean magnetic field is what is leading to the Alfine waves, right? KB0. That's what you also used for time scales. But
yeah,
if you look at Alfine wave, which is, so I argue in a multi-scale manner. So let's look at Alfine waves in 10 scales, 1 millimeter to 1 meter. Then 1 millimeter Alfine wave, the wavelength, these are wavelengths. 1 millimeter Alfine wave is going to see a mean magnetic field of 10 millimeter Alfine wave, not a 1 meter Alfine, basically not the mean magnetic field. So if you track, then you look at local slopes, not the mean slope of the mountain. So the local mean magnetic fields are important. So in fact, there are, so local mean magnetic field. In local mean magnetic field, I could show by field theory that scales as K minus K 1/3. B0 goes as K 1/3. No, K minus 1/3. So if you put B0 as K minus 1/3 and put in the Kraichnan formula, then we recover minus 5/3. Of course, I assume isotropy. To do this calculation, if I put in isotropy, I could not get much distant. So I assumed isotropy and put that stuff. So it is K B0 to the half K minus 3/2, right? So I put B0 as K dependent is minus 1/3. I showed it by a renormalization group. So that makes it correction minus 1/6 to the spectrum, and that gives you 5/3. Of course, the idea would be to incorporate for with mean magnetic field being there and some isotropy. But I think if you put in very strong magnetic field, like 5, then it is probably quasi 2D. Then anyway, nothing works, neither 5/3 nor 3/2. So what do you say about this? I mean, this is your take on this.
Yeah, I don't think the 3/2 is correct either. And I think Kraichnan was happy to acknowledge that the isotropy assumption about the K dot B0 being approximately K times B0 was a mistake, and that he shouldn't have done that. Nonetheless, it was very influential, and it was progress at the time. You could sort of view the next 20 or 30 years subsequent to that as increasing acceptance that anisotropy plays an important role in MHD. It's more complicated than isotropic Navier-Stokes or something that's closer to rotation or whatever.
Yes.
And the wiggle room for the 3/2, I guess, is the Boldy-Rev stuff, which is a very different argument, unrelated to Kraichman's argument, really, why you get it. But I also don't find that particularly convincing. I prefer, I think Berezniak may have it right, that there's you might see 3/2 if you had very, very large Reynolds numbers. You might see a transition region where you had 3/2. but it would go away and become 5/3 and small enough. So, and I think neither of those are really about the local mean field strength scaling, which the point you raised about your nice paper. That's an additional argument for why 3/2 is unlikely to be seen. Yeah. Except perhaps in the sparse mode too.
Yeah.
If you could read.
So, okay. So right now we are trying to do some work on anisotropy with Riddhi. So he had some simulations. So with, in fact, Somdeep, he is one of the PhD students in our group. So he will analyze that and do that. We normally want to look at the energy flux. Is there inverse cascade or not with strong magnetic field? We did find some of it in earlier work. There was a work. I'll send you some papers.
Sure.
Sita Sundar. She did in Alexakis. Alexakis had the data and we analyzed it, and we found some inverse cascade in the velocity field. So I mean, so if you look at the K parallel equal to 0 mode, that is not Alfine wave anymore, right? Because the K dot B naught term just disappears.
Yep.
In that Z plus Z minus equation, or all equations, in fact, K dot B naught is 0. So it is more of a nonlinear equation after that. And I strongly suspect that there is a two-dimensional effect will play a role. And so that work was, I mean, the postdoc had left, so we didn't really do it in thorough study. But that will be good thing to, I mean, that's what we plan to do now. I mean, look at the flux. But so, yeah, so I think we'll send you the paper. And if you have some ideas on, so do you get any kind of inverse cascade or some, well, of course, you're not analyzing the flux, but if you look at maybe.
I haven't looked at it in these simulations, no.
Yes.
There might not be, I mean, there would be space because we're starting at K equals 10 for the initial conditions. So there would be a decade of wave numbers to see it. But the Reynolds numbers are so low that it might run out of steam before it gets started.
Okay. So, but yeah, look at the flux if you could, because your simulations is supposedly 1000 cube. You could get, what about the spectrum? Did you plot them just in case? I mean, the isotropic spectrum, all three component in your simulation with B naught equal to 1 and 0 and 5?
Yeah, so the inertial range is not long enough to be confident of what the slope is.
I see.
If I want to talk about an inertial range slope, I'd like to have at least a decade of scales.
Yes.
And we're getting less than that in these simulations.
Yeah. That's true. So one more thing is this alpha ratio being half or close to half. So solar wind is basically decaying turbulence. So is your simulation decaying or forced? The one where you're analyzing the half part?
Yeah, those ones at the end, all of them were decaying. So we were just looking at those were the Alfine ratios around the time of maximum dissipation.
Okay.
In the simulation.
Right.
Non-linear time or two.
So what we had, I mean, there was work done with Belgium group, this by Karate et al. So his student, Deblicki, he did this. So what we found that if U squared was bigger than V squared, so we start initial condition. We just make large U squared, but we are always forcing isotropically. Initial condition is isotropic, not forcing. Initial condition isotropic, and let go. Both isotropic U squared and isotropic V squared. Large scale, we put in lower number modes and let go. And then if U squared was much bigger than V squared, then U squared comes down. But if V squared is more than U squared, then V squared comes down. And they like to go around half, 0.4, half, 0.6. So that was what we found in that work. And we felt that it's kind of energetic. So there is if U is more than it used to be, or B is more than it used to U. Yeah, but I think you have a good point about slab and 2D decomposition. It's a good. I mean, I think it's interesting way to analyze what is dominating this dynamics. But in solar wind, is it? I mean, it's hard to get. Yeah, but because you have only one probe along 1D.
Yes.
That's
yes.
That makes it a. But in your
So
simulation,
one idea for the solar wind fluctuations is that it's kind of spaghetti-like.
okay.
That you have these flux tubes. So there's a lot of structure, different width, different radius flux tubes.
Right. Right.
But that are wiggling slowly
So
along the direction.
maybe Sean, you can turn off your PPT so that we can see you in a bigger screen. If we need it, then so let's just yeah. Okay. So
you have
you speak
a big flux tube and then a small one next to it, and they have some extension in the direction towards us. So that's kind of the parallel axis. So as you cut across that, you see quite a lot of structure. So it's quasi two-dimensional in that sense. I mean, it's not that they're perfect flux tubes; they wind a little bit.
Okay.
I see. That's one model. Borowski likes that model. The Italians like it because it's like pasta.
I see. So I need to see. Solar wind. I have not been doing it. Now I want to get back, at least to some degree. With Riddhi, we have a regular meeting, and so which is your 20 paper, Will? You said 20.
So that was, it was a review of MHD phenomenologies and critical balance in particular. It was in APJ, Astrophysical Journal.
Okay, I'll look at it. Yeah. Great. I guess the audience.
I'll send you a copy if you want.
Yeah, maybe. I mean, okay, I can find it, of course, but yes, if you just send me that paper and some more papers connected to today, especially that K parallel. Once you write it up, you can send me that one.
Definitely.
Yeah. So I think we have a lot of overlap. So I want to get back to MHD now. Great. So any questions from the audience? One more call, then we can thank the speaker and stop today. I guess, so we have less audience today. Okay, Sean. So I think we will let you. I mean, I guess you had your dinner. I don't know, but
yes, I have.
You had your dinner. Great. Okay.
Okay. Well, thanks again. Really enjoyed this, and
thanks for being a very nice talk, and we'll think about it and get back to you with some questions and some more discussions. Great. Okay. Thanks to everyone for attending this seminar. So next week we'll meet again, but next week will be 6 p.m. Okay.
Right.
Great. Okay, but you'll miss it. I'm sure you can't be here.
It's getting pretty late by then. Yeah.
Yeah, I know. I agree. Okay, Sean. See you. Thanks again. Bye.
Okay. Bye, Mandra. Bye everyone.
Bye.